everyone, today we are looking at 7.5, which is proportional relationships in our triangles. So this whole chapter we've been talking about similarity, and we're going to build a little bit off of that today. So the first thing that we're going to talk about is our triangle midsegment theorem. Now, what the midsegment of a triangle is, it is a segment that joins the midpoints, all right? So if I look at this triangle here, X is a midpoint because these two pieces are congruent. Y is a midpoint because these two are congruent. Z is a midpoint because these two are congruent. So each segment that connects those two midpoints is called a midsegment. Your triangle will have three mid-segments within it, and those three segments will form what we call a midsegment triangle. So now the question is what do we know about midsegments and their relationships within the triangle? So if I look at segment GH here, okay, this is a midsegment of this triangle. And what my theorem is going to tell me is that my midsegment is going to be parallel to the side it doesn't touch, and it is also going to be half of the length. All right, so our midsegment is half the length of DF. So similarly, when we did trapezoid midsegments earlier, we said our trapezoid midsegment was half the length of both bases. Well, now we just have basically one base, so our triangle midsegment is half the length of this. The other way that I can write this is 2 times my midsegment is equal to the length of the parallel side. Okay, so either way, I can double my midsegment or I can cut the side length in half, whichever works best for whatever you're doing. I tend to like to multiply the midsegment by 2. Now, why are we looking at this here? Okay, well, I know that if these sides are parallel, these angles are congruent, these angles are congruent, okay, because they are corresponding angles in parallel lines. I also know that this length here is going to be half of this length here, so this little triangle will be similar to the bigger triangle. And my similarity ratio from little to big will be 1/2 because this is the same length as this one. So this is half of this. All right, so these two triangles are similar, so it fits right in with what we're doing. So let's take a look at how we use this. All right, first things first is I'm going to highlight UV and its midsegment, or its side that goes with it. So I'm highlighting the midsegment and the side that it matches up with. And I'm going to do the same thing here. We're given this midsegment, and it'll line up with this side and be parallel to this side here. So the first question is, I want to know the length of UW, which is right here with this pink one. So my midsegment is half the length of the parallel base. My parallel base is ST. So UW is going to be half of 7.4. Oop, getting sticky here. 7.4. There we go. All right. And half of 7.4 is 3.7. Remember, if there's a unit, you should include it, but there's not in this particular picture. All right, the next what we're going to look at is the measure of angle SVU. So SVU is this angle right here. Well, if we look at the fact that this is a midsegment and it is parallel to this side over here, all right, that means I've got parallel lines. And when we have parallel lines, we look at things like corresponding angles or alternate interior angles. And if I look at it this way, this angle here and this angle here are corresponding angles. If you're struggling to see that, because sometimes it's hard to see things when they don't look the way you're used to, I'm going to just take this over here for a second and I'm going to turn it. So that way we're looking at our parallel lines here and here. And now we see that SVU is here and we've got this one over here. So those are our alternate interior angles, which means that the measure of angle SVU is going to be 41 degrees. All right. If you have any questions on that, go ahead and write it down. little off, but all right, so let's go ahead and look at another example. I want to find the values of x and y. So what I'm going to look at is I'm going to look here inside the triangle where we start. Okay, I've got this side's going to go with this side, and I want to find y, and y is here, and it's going to go with this side. So as I look at this, what I want you to notice is as I look at my y midsegment with this one, notice that this has a y and this has an x. So then we look at our x one. This one has an x and this one has an x. So we're going to start with x because then I can just plug it in. All right, again, I like to double my midsegment, so I'm going to do 2 times my midsegment, which is mn, is going to be equal to the side length across from it. Again, you're welcome to do that mn is half of de. They are the same thing. All right, but when I plug in what I know here, I'm going to get 2x is equal to 4x minus 10. Subtract 4x from both sides, I'm going to get negative 2x equals negative 10. And I divide by both sides by a negative 2, I'm going to get x is 5. All right, so then we're going to look at finding y. All right, so I'm going to do 2 times the midsegment that contains y, which is MO, is equal to the side across from it that it does not touch, which is FE. All right, so this is going to be 2y is equal to 2x plus 12. Well, we know what x is. We just found that x was 5. So then this is going to give me 2y is equal to 2 times 5 is 10, plus 12 is 22. And then I divide both sides by 2 to get y is 11. Again, if you have any questions on midsegments at all, go ahead and write those down now. All right, the next theorem that we're going to look at, which is similar to this one, in the sense that we are still looking at that line that's going to be parallel. Now the difference is we're not talking about the midsegment. It can be anywhere in here, not necessarily at the midpoint. But we're going to be looking at these being parallel. So again, I'm going to say, okay, I know those are congruent and they share angle B. So this triangle is similar to this triangle by angle-angle similarity, which means that those side lengths are proportional. Now, what the side splitter does is it lets us say that, okay, I can say now that this piece, instead of being proportional to this whole side, which is still true because they are similar, but I can say now that this piece is proportional to this piece, and that this piece over here is proportional to this piece. So what I often tell you guys to do with this, and please do it, it'll make your life so much easier, is we're going to draw a fraction bar and an equal sign and a fraction bar. And look what we're going to have. We're going to have AM, or we're going to have MB over AM and BN over NC, which is exactly what we have down here. Okay? So, any questions on that? Let me know. And this is something that works even if you turn your triangle. If you turn your triangle this way, this still works here. So whatever these are. Okay? It goes left, right. It goes up, down. The only thing you cannot do is set up anything in the diagonal. I cannot set up a portion with BN and AM in the same fraction. So let's take a look at what that looks like. Okay? So with this one, I want to find the length of CY. So I'm just going to call CYX here. And I am going to set up my proportion. I'm going to draw a fraction bar and an equal sign and a fraction bar. So what I'm going to set up is 4 over x is equal to 9 over 10. All right, we cross multiply. We get 9x equals 4 times 10. So 9x equals 40, and we divide both sides by 9 to get 40 over 9, and we leave that alone because we don't have any context, and we're not told to round the nearest anything. So just leave it as 40 over 9. Now, let's take a look at what happens if I set this up a different way. If I take this triangle and I rotate it, all right, and we set it up this way. If I set up my fraction bar, my equal sign, and my fraction bar, if this is my x, I'm going to have 9 over 4 equals 10 over x. Well, look what happens when we cross multiply. I'm still going to get 9x is equal to 40. So it doesn't matter. Like, I could also flip this entire proportion upside down. As long as you cross multiply and you're getting the same thing as this line here, then whatever proportion you have set up is correct. All right? So as long as 4 and 10 are in a diagonal, 9 and x are in a diagonal, your proportion is correct. All right, with this one, we're going to verify that they're parallel. So I'm going to do a fraction bar, an equal sign, and a fraction bar. And the key with the differences here is I want to know 21 over 15, is that proportional to 42 over 30? So what we want to look at is how reducing these two fractions, if they reduce to the same thing, then we know that those lines are parallel. If they reduce to different fractions, then these lines are not parallel. So what we're going to do here is 21 and 15 are both divisible by 3, and 42 and 30 are both divisible by 6. So when I do my first fraction and I divide by 3, 21 divided by 3 is 7, 15 divided by 3 is 5. Okay, over here we both have commons of 6, so 42 divided by 6 is 7, 30 divided by 6 is 5. So they are equal, which is what we want. So we know that yes, MN is parallel to KL. All right, again, because those are proportional. So if you have questions on that, make sure you write it down on your notes and ask them in class. All right, the next thing we're going to look at is the corollary to the side splitter, which basically says we don't have to have triangles. All right, we can just have parallel lines, and these are still going to be proportional. I can still set up AB over BC equals DE over EF. All right, so that's the big key here, is that because what's going to happen is eventually these will intersect to form triangles. But it works even if they won't, and these lines are parallel, because they would be the same length. All right, so side splitter works in triangles and in just straight parallel lines. So let's take a look. All right, I have an artist is using her perspective to draw a sketch of a row of parallel trees. And then she checked her distances and measurements by measuring the distances between the trees. I want to know what LN is. So what I'm going to look at here is LN is this whole length. So I'm going to ignore the fact that there's a line here, and I'm going to look at the whole length of BD. Well, BD is 1.4 plus 2.2, so it's 3.6. And now I'm going to set up my fraction bar, my equal sign, and my fraction bar. So what I'm going to get here is 2.4 over 2.6 is equal to the whole length of BD, which is 3.6, over what I'm looking for, which is LN, which is X. All right? So I'm basically just looking at this whole chunk. Okay? So then from here we cross multiply. We're going to get 2.4x equals 2.6 times 3.6. Okay, 2.4x. Now, 2.6 times 3.6 is going to give me 9.36. And when we divide that out, that is going to give me 3.9. Now, our units of our drawing are in centimeters, So please make sure that you include that as well. All right, so if you have questions on that, again, please write it down and let me know. All right, the last thing that we're going to look at today is the triangle angle bisector theorem. And what's going to happen here is if I have a line, a segment, or a ray that's going to bisect an angle in a triangle, then we're going to end up getting similar pieces in here as well, things that are proportional. So what I'm going to do is I'm going to kind of take another one of these and just show you again. We're going to do the same thing that we did with the side splitter. And we're basically going to draw a fraction bar and an equal sign and a fraction bar. So what I can do is I can put a fraction bar here, an equal sign here, and a fraction bar here. And I have UV over UX is going to be equal to VW over WX. Okay? Or I could run it this way, a fraction bar, an equal sign, and a fraction bar, and say VW over VU is equal to WX over XU, which is what this one is upside down. All right, so you can go side to side, you can go left to right. Again, you're never going to put this one and this one in the same fraction because that's kind of going across the diagonal. But otherwise, when you're looking at this, it's kind of set up in the fraction for you. Just make your life easier. So when I look at our example, I'm going to do my fraction bar, my equal sign, and my fraction bar. So I'm going to set up 10 over 14 is equal to x plus 2 over 2x plus 1. Now, I notice here that 10 over 14 is the same thing as saying 5/7. You can reduce here if you would like to, or you can wait and see what happens at the end and divide it out. Either way is perfectly acceptable. I like to deal with smaller numbers, so I'm going to go ahead and do this with the 5/7. You will get the same answers. Again, guys, anytime you have binomials in your proportion, take a half a second and put parentheses around it. So then when we cross multiply, we're going to get 5 times 2x plus 1 is equal to 7 times x plus 2. Remember, we distribute, so 5 times 2x is 10x. And 5 times 1 is 5. 7 times x is 7x. And 7 times 2 is 14. So then from here, we're going to subtract 7x from both sides, get 3x plus 5 equals 14. Subtract 5 from both sides, we're going to get 3x equals 9. And divide by 3, we're going to get x is 3. Now again, we need to stop and look and see what our directions say. I want to find the length of RV and VT, so now we need to plug it back in. So RV is going to be 3 plus 2. So RV is 5. And then VT is going to be 2 times 3 plus 1. So 2 times 3 is 6, plus 1 is 7. So now we have 5 and 7, which is what our other side reduced to. So we have 10 over 14 equals 5 over 7, and yes, it does. So that's a good place to check and make sure that both of your fractions that you set up reduce to the same thing at the end. All right? Again, if you guys have any questions, make sure to write it down. Hope you guys have a great night, and we will see you later.